Hello everyone! Today we are going to tackle a question in organic chemistry that, let me tell you, confuses so many students. But don't you worry, by the end of our little session today, you'll find this concept crystal clear. I am very sure of it.
So let's just jump right in. Now have a look here. We have an alcohol and we have a phenol. At first glance, you might think, array, they are so similar, right? I mean, both of them have that famous OH group, the hydroxyl group. But you know, chemistry is full of surprises. So the big question we need to answer is this. If they both have the same functional group, why on earth do they behave in such completely different ways?
And I'm not talking about small differences. These are massive differences. Just look at this comparison. Your alcohol, something like ethanol, is totally neutral. It loves to do substitution reactions, and you can oxidize it quite easily. But then you have phenol, completely the opposite. It's acidic. It stubbornly resists substitution, and it also resists oxidation. So you see, something very, very fundamental must be going on here to cause such a personality clash, even though they both have that same OH group.
All right, so to solve this chemical mystery, we need to think like detectives. We need to look for clues. And the very first clue, the most important one, isn't the OH group itself. No. It's where that OH group is attached. It's all about the location.
Okay, first up, let's look at alcohols. Now, this definition you see here is super important. Please pay attention. For any compound to be called an alcohol, the OH group has to be attached to what we call a saturated carbon atom. And what does saturated mean? It's simple, really. It just means that carbon atom is busy forming single bonds with 4 other atoms. That's your classic sp3 hybridized carbon.
Now, let's look at phenol. And here is the big difference. In a phenol, the OH group is attached directly to a carbon atom that is part of a very special, very stable structure, you know it, the aromatic benzene ring. And the carbons in this ring are sp2 hybridized. They have those double bonds. So you see, it's not just any carbon. It's a carbon that's part of this exclusive club, the aromatic ring. This direct connection is the key to everything. So, are you ready for the big reveal? We have our clues, right? We know where the OH group lives in both cases. The whole secret, the entire explanation, comes down to its chemical neighborhood. It's all about the company it keeps, and this one difference in its surroundings completely changes its personality.
Now, I want to be absolutely clear about this. All this time in chemistry, you've been taught to focus on the functional group, right? So you might think the OH group is the main character here. But you know what? The secret is not the OH group itself.
It's the super powerful, all-important influence of the aromatic ring. That is the real hero of our story today. This ring is the game changer.
So, how does this ring work its magic? Well, here's the science. That big aromatic ring in phenol is very electron-rich, and it's a bit of a bully. It actually pulls electron density away from the oxygen of the -OH group. This effect, this spreading out of electrons, has a very famous name. It's called resonance. Now, because of this resonance, think what happens when phenol decides to give away its proton, the H+. The negative charge left behind on the oxygen isn't stuck there all alone. No, the whole ring helps to share that negative charge. It stabilizes it. It's like the whole family is sharing the burden. And because the resulting ion is so stable, the proton can leave very easily. And what do we call something that gives away a proton easily? Exactly, an acid. Now, poor alcohols, they don't have this fancy aromatic ring to help out. There's no resonance, so they just hold on tightly to their proton, and that's why they stay neutral.
Okay, I know what you're thinking. Resonance. Sounds a bit complicated, right? Don't worry. Let's use a very simple story, an analogy, to make sure this idea stays with you forever, especially when you're sitting in the exam hall.
So I want you to imagine. Think of the alcohol molecule as just a normal person, living an ordinary life. But the phenol, the phenol is different. The phenol is like a member of a noble royal family.
Let's break this down. Our alcohol, the normal person attached to a simple carbon, has a neutral personality. It's openly reactive. But our phenol is part of this noble family, which is, of course, the aromatic ring. This family connection gives it a special status, a high status. And that status is our analogy for resonance. This status makes the whole structure very stable. It's more willing to let go of something minor, like its proton, because it knows the family, the ring, is powerful enough to handle the situation afterwards. That's why it's acidic. It's willing to donate. Okay, so this theory is all very nice and the analogy is helpful, but how can we actually see this difference in the real world, like in a chemistry lab? Well, let's look at a very simple test that gives us visible proof of everything we've been talking about.
Okay, let's take a common indicator, phenolphthalein. Now, if you take some ethanol, which is an alcohol, and add a few drops of this indicator, what happens? Nothing. It stays completely colorless. This confirms that ethanol is neutral. But, and this is the exciting part, if you take a solution of phenol and add the same indicator, the solution immediately turns a beautiful pink color. And that pink color is the undeniable visual proof that phenol is acidic.
And believe me, this isn't just some random fact for your lab practicals. This acidic nature of phenol is hugely important in the real world in industry. For instance, have you heard of Bakelite? It was one of the very first plastics ever made. It's made from phenol and formaldehyde. And the only reason that reaction works, the reason you can make the strong polymer, is because of phenol's unique acidic character. You simply could not make Bakelite using an alcohol. It just wouldn't work.
And there you have it. Case closed. We have solved the mystery of the OH group. So just before we finish, let's do a super quick recap of the main points, the things you absolutely must remember for your exam. Just lock these 3 things in your mind. First, the core idea. The aromatic ring is the hero. It's what makes phenol acidic, while the poor alcohol without a ring stays neutral. Second, the mental image. Just picture that big, stable aromatic ring holding hands with the OH group, sharing its burden through resonance. And third, the real-world example. Remember that simple lab test. With an indicator, the phenol solution turns pink, proving it is acidic. Simple.
And that's really it. That's the whole story. If you can just remember that one core idea, that one mental picture of the noble family, and that one pink color test, I promise you this topic will feel so much lighter and easier in your exam. You can do this. All the very best.